Okay, but in this lesson, we got to talk about a lot of things to do with sort of how those factors that affect climate that we talked about work. Okay, like why being close to the ocean can regulate your climate. Okay, why being behind a mountain barrier affects your climate. Okay, we got to look at energy transfers, and this might seem familiar, but like convection, conduction, and radiation. You learned about those in junior high. Okay. You know, albedo and kind of actually truly global systems and energy, okay, in this particular lesson. So a lot of stuff, okay, and I'll tell you sometimes when something is super important and needs to be highlighted or written down. Okay? So first thing we're going to do is look at the three parts of the Earth. Okay? The three parts of the Earth are the atmosphere, the hydrosphere, and the lithosphere. So that would be the gases surrounding the Earth, the water on the Earth, and the rocky solid part of the Earth. Okay? All three of those things have a role to play in how energy is absorbed, how energy is converted, how energy is transported or transferred from one place to another. And we're going to look at that because that's a big part of one of the big questions, at least on your unit exam. Okay? All right, second thing, how energy on Earth is absorbed, used, and reflected. These are essentially the three things that can happen to light when it strikes the Earth's surface. It can be absorbed. If the light is absorbed, then the energy of that area goes up. That usually means the temperature of that area goes up. Okay? It can be used. Sometimes we also say instead of used, converted. Right? There's only one thing on this Earth that can directly use solar energy and convert it into other forms. What is it? Or what are they?
Stars?
No, on Earth. One thing that can use solar energy on Earth and convert it directly into something else. Plants. Yep. Okay. So plants can use or convert this energy through the process of photosynthesis. Okay. This is the only way that energy becomes other things on Earth. Okay, is through photosynthesis. And obviously then it can also be reflected. And we're going to talk about what determines how much gets absorbed, how much gets converted, how much gets reflected. Okay, and then understand how the energy and the Earth interact to produce the conditions necessary to support life. Okay. All right, first thing we're going to talk about is the atmosphere. Now I'm going to tell you right off, and you might want to write this, this is the most important part of the Earth in terms of the transfer of global energy. Okay? I mean, we're talking about the three parts of the Earth, the atmosphere, the hydrosphere, and the lithosphere. Well, the atmosphere is the most fluid, okay, part of those three parts. It's in contact with all parts of the Earth. Okay? It easily moves because of wind and the laws of thermodynamics. So the atmosphere is responsible for more energy transfer than the other two parts are combined. Okay? It plays just this huge role because of how fluid it is and because it can move so easily. Now, you're never going to be asked by me about the layers of the atmosphere because their names are not really important. Okay? But we do need to understand that the atmosphere is stratified. That is, it has different layers. Okay? The layer closest to the Earth is the one that's more important. That's the troposphere. Okay? That's where the air is the thickest. It's where life can be supported because there's sufficient atmospheric pressure and oxygen and nitrogen and all that good stuff. As you go higher up, okay, you get into the stratosphere. And the stratosphere is still important. It's where a lot of weather and the jet stream and stuff like that happen. Okay? So it's still important, but it's not where anything really lives, okay, per se. All right? Now, can we stand on the Earth's surface and be in the stratosphere? There are a few places on Earth where you can do it. Okay? Everest, K2, okay, are two of the biggest ones. Right? Can you live on the top of Mount Everest or K2? For short periods of time, you can. But it is not called the death zone for nothing. Okay? Once you get above a certain altitude, you're in what climbers refer to as the death zone. It basically means you've exited the troposphere and entered the stratosphere, where the atmospheric pressure is no longer sufficient for your body to work properly. You lose fluid easily, rapidly, just by breathing. Okay? It's cold. Okay? And there is not sufficient oxygen for you to properly oxygenate your blood or carry out the chemical reactions that allow you to release energy from your food. Okay? So this is why lots of climbers end up dying up on the top of these mountains. Okay? If they get stranded up there for any length of time, they get hypothermia and they die. Okay? Simply because they don't have enough oxygen. Okay? And the chemical reactions that keep our body going just slow down to the point where they're not enough to keep you going. Okay? So if you've ever seen any of those like Everest documentaries, right? They've got they actually use the corpses as markers. It's very grisly. Okay? There's like green boots and like Rainbow Valley where like most of the bodies end up falling. So there's all these brightly colored parkas from. It's really morbid. Okay? And so yeah, what happens is these people, they're carrying oxygen, they go up, they get stuck in a blizzard, whatever, they run out of their supplemental oxygen, their tank runs dry or whatever, and then they just get tired. And they sit down and they tell themselves, I'm just gonna sit down, I'm gonna take a little nap and I'll be good. Except that they don't wake up from the nap. Okay? Because they're not good, okay? Their oxygen is just so low that they just can't keep going. Okay? And that's when they get frostbite. Okay? The ones that survive usually have no fingers or toes afterwards because frostbite sets in because again, your oxygen is just not sufficient enough to keep your body running. Okay? So you're not gonna have anything really living above the troposphere because the atmospheric pressure is too low. That means the amount of gas above you is not sufficient to push down on you and create enough pressure. Right? This is why if you go into space and you like open your visor or something that you'll die. Okay? Because it's a vacuum. There's no pressure. Okay? What keeps all the stuff that's in our blood is the weight of the gases from the atmosphere above pushing down. Okay? The higher up you go, the less pressure there is. So for example, here at 1,100 meters above sea level, water boils at about 96, 97 degrees Celsius. What's it supposed to boil at? 100. At the equator, at sea level, okay, water boils at 100 degrees Celsius. But here, there's less gas above, so water evaporates more easily. Okay? So it gets to its boiling point even earlier. Okay? The guys that are eating like ramen on the top of Mount Everest, in their little tents, they're hunkered down, they make soup. That soup, they're eating it boiling because it's boiling at like 65 degrees. Okay? Because there's so little atmospheric pressure that it just boils away. Okay? The same thing is true on the surface of Mars. That's why there's no liquid water on the surface. There's not enough atmosphere to hold it there. Anytime water appears, it boils off really, really quickly. Okay? Does that sort of make sense? So the atmosphere plays this very important role in holding everything kind of in place. And the fact that it can move, because it's just gas, helps to transfer energy from one place to another. Okay, so the atmosphere plays a critical role in maintaining the Earth's temperature, which in turn has a profound effect on the Earth's climate. So if we look at our two nearest neighbors, that would be Venus and Mars, planetary neighbors. We're like the Goldilocks of the three. Mars has too little atmosphere, and so it can't retain heat, and so it's very, very cold. Venus has too much atmosphere and retains way too much heat, and as a result, on the surface of Venus, it is like 400 degrees Celsius. It's hotter than the inside of your oven on the self-cleaning cycle, because it has got too much atmosphere. Earth, we've got it just right. We've got the right thickness, and it retains heat, but lets enough get away that we don't roast. We definitely have a greenhouse effect. It's actually important that we have it. We don't want it to get worse. But it's important that we have it because it traps energy and that maintains the conditions necessary for life here. Now, when solar radiation strikes the Earth, three things can happen to it. It can be absorbed, it can be reflected, or it can be, what was the third one? It's on the first slide. I told you to write it down. Plants do it.
Photosynthesis?
Yeah, photosynthesis. Convert it, use it. Photosynthesis is the process that makes that happen. Now, what determines how much of that happens is the atmosphere and the Earth's surface. If we got light coming in from the sun, some of it hits the top of clouds. Tops of clouds are white. They're highly reflective, so it just bounces off. goes back out into space. Some of it tries to travel through the atmosphere, but it gets scattered. Okay? Certain wavelengths, especially blue, tend to get scattered on normal days. That's why the sky is blue. Because blue light gets scattered all over the place and makes the sky appear blue. Okay? You probably got told by some well-meaning person that the sky is blue because it reflects the ocean. Okay? You got told that? They were wrong. Okay? What color is water? Clear. Therefore, the sky can't be blue because it reflects off the ocean, which is clear. Okay? The ocean looks blue because it reflects the sky. It's actually backwards. Okay? The ocean is clear. So the sky is blue because it backscatters blue light, unless it's really smoky. Then what color does the sky look? Gray. Yeah, or even sometimes brown and orange, right? Like it gets these weird colors because if you get more particulates, smoke and ash and things like that in the atmosphere, different wavelengths get scattered. Okay? That's why at sunset and sunrise, the sky appears kind of orangish red. Okay? Closer to the horizon, there's more particulates in the air. Okay? And they scatter the longer wavelengths of like orange and red and things like that. Okay? On a really smoky day, that's what gets scattered because that's what's there. Okay? That making sense? Okay? So that stuff that gets scattered, okay, that stuff that gets reflected, doesn't warm the earth at all because it's not being absorbed. Okay? Now, as the light goes through the atmosphere, it's going to hit the earth. When it hits the earth, again, one of three things can happen. It can be reflected, it can be absorbed, or it can be converted. The only time it's going to be converted is if it hits what? Plants. Okay? Are there lots of plants? Yeah. Okay? And there's even photosynthetic organisms in the ocean. So even if it hits the ocean, it still could be converted. There's lots of algae and things like that that are in the ocean. Okay? Now, what determines how much of it gets absorbed versus how much of it gets reflected is this. This word is really, really important. Okay? Because I've now said like 3 times today, the 3 fates of light when it strikes the Earth's surface. Absorption, reflection, and conversion. There's a question on your unit exam that's going to ask you about this. And albedo needs to be part of your answer. Okay? Albedo is the reflectivity of the Earth's surface at a given spot. The higher the albedo, the more reflective that part of the Earth is. Okay? If it reflects a lot of the light, very little of the light is being absorbed, and that means very little energy is absorbed by that particular area. Okay? If the albedo is very low, okay, then a lot of the energy gets absorbed, and the energy is going to change, and the temperature in that area will go up. Okay? So white is the most reflective color. It reflects all wavelengths of light. So if something is white, it has an incredibly high albedo. So in the wintertime, here, we have the lowest angle of incoming solar radiation. We have the least amount of hours of incoming solar radiation, and we're covered in snow. How much energy is being absorbed by this area in the winter? A lot or a little? A little, yeah. Okay, we've got the 3 worst things for warming an area going on. Okay, we've got lots of snow which reflects basically anything that comes in. We're hardly getting any intense sunshine in the first place, and we're only getting what we get for 6 hours a day. That's why it's so cold in the winter. Okay, it takes a long time to get rid of the snow. Now, if you want snow to melt faster, what do you do? The town does this all the time in the wintertime on the roads.
Put like rocks or like little sand bits in it?
Yeah, they throw sand on it. Okay? Sand does 2 things. It helps us gain traction because it's gritty, okay? But it also darkens the snow, which lowers its albedo. It's also why we make our roads dark in color. Okay? It's not by accident that our roads are dark in color. Okay? We want them dark because then they'll absorb lots of solar energy and help to melt the snow off the surfaces more quickly. If you go to California, they don't even use asphalt on most of their roads. They build most of them out of concrete that's very light in color because they don't want their roads to absorb lots of solar radiation or they'll get soft. Okay? You ever notice around here, like at intersections, there's grooves? Okay? The reason for that is in the summertime, the asphalt gets hot and soft, and heavy trucks can actually push it downwards. Okay? In California, that can happen all year round, and it can really be bad for your roads. I remember as a kid, we got a flat tire on the way to Disneyland, and my dad tried to jack up the truck, and the jack sank into the pavement. Okay? Like, the pavement gets really soft when it's hot. Okay? So it's not good. Right? So we want to have a low albedo means a lot reflects. So if we're looking at this diagram here on the right, okay, in the wintertime, we have a high albedo situation. 85 to 90% of the incoming solar radiation is going to bounce off because everything is covered in snow or ice. Okay, about 10 to 15% is going to be absorbed by an exposed rock or a tree that it's probably not carrying out photosynthesis because it's frozen, okay, but it's still dark in color. In the summertime, the situation is almost completely flip-flopped. Okay? In the summertime, there's no snow, so 70% of the incoming radiation is being absorbed by dark colors. Okay? 10% of it's being reflected off of water bodies that are now obviously not frozen. Okay? And about 20% gets reflected off of light-colored materials that may or may not be present on the ground. Okay? Now, in this 70% of absorption is also the conversion that's going on. Okay? So the conversion part would be included in that. Okay? Everybody with me there? All right. Here's how your question on your exam for this concept is going to go. I'm going to go on to Google Maps, satellite view, and I'm going to snap a picture of an area. Okay? And maybe it'll be a picture of an area in the wintertime, or maybe it'll be a picture of an area in the summertime. And I will put that picture on there and I will say, tell me what's going to happen to light when it strikes this part of wherever. Okay? And you're going to tell me 3 things are going to happen. What are those 3 things? Well, if we don't know that after I've said it like 10 times already today.
How much you think is going to be absorbed, used, or reflected?
Right. Those are the 3 things that can happen. Okay? Used, reflected, absorbed. Those are the 3 things. Okay? You look at the picture, and if it's all snow, you're going to tell me the albedo of this area is very high. So most of the energy that's coming in is going to be reflected. There appear to be very few active plants in this area, so very little of the light is going to be. What do plants do? Starts with C. Converted by photosynthesis. Okay, so very little will be converted, okay, and very little will be absorbed because there are very few dark colored objects around that could absorb the energy. Okay? If I showed you a picture of like the tropical rainforest in Brazil, okay, then you would probably say, well, a lot of the energy coming in is going to be converted because there's a lot of green plants in this area. What's not converted is likely to be absorbed because everything else is dark in color and very little of the energy will be reflected. Okay, you guys follow what I'd be looking for there? So you've got to talk about those 3 things. That would be like 3 marks, basically just writing down those 3 things. Okay, and then explaining to me why would be the other 2 marks on that question. Okay, so being able to apply your knowledge of those 3 things, okay, the 3 fates of light, okay, to that situation. Is that a pretty easy question? Okay, all you have to do is look at the picture and tell me, okay, and use the word albedo. Nobody wrote that down. Okay, you should use the word albedo in the answer to that question. Okay, so that's what we see in this diagram here. It comes in, it can be absorbed by the earth, it can be reflected. Some of that stuff that's reflected gets a second chance, okay, because it gets trapped by the earth's atmosphere, the greenhouse effect. Okay? Greenhouse effect is not all bad. We need it. If it wasn't here, earth would be a snowball, right? So we have some greenhouse effect. That means some of that stuff that gets reflected off the earth bounces off the greenhouse effect and comes back. Okay? Gets a second chance to be absorbed. Right? That's what brings the temperature of the earth up. If that greenhouse effect gets worse, then obviously the earth will get warmer and warmer and warmer. Okay, questions on that? So albedo and the 3 fates, gotta know. Okay, so we talked about the gases present in the atmosphere. Okay, these are our greenhouse gases: carbon dioxide, CFCs, okay, methane, ozone, nitrous oxide, and believe it or not, it's not mentioned here, but water. Good old water vapor is also a greenhouse gas. Okay? So all of those things are important and not necessarily bad. okay? If they're, keeping the Earth's climate livable. Okay, so this is just showing that in a diagram form. Oh, and the other day I found this picture kind of the rain shadow effect. Okay, so this is Mount Robson. Okay, I had a picture of it in the altitude slide of that other lesson. Okay, and every day you see this happen at Mount Robson. Okay, there'll be a nice clear blue sky, and then all of a sudden a cloud will enshrine the top, and then it'll disappear, and the top of Mount Robson will be covered in perfectly pristine snow. Okay, and it only takes like 20 minutes. Okay, be clear, you see the top of the mountain, and then the top of the mountain disappears for 20 minutes. This cloud shows up, and then this cloud disappears, and the top is covered in snow. Okay, it's because Mount Robson is so high that occasionally a warm, moist air mass runs into it and gets forced up and over, and as it gets forced up, it gets cold enough that it just drops all of its moisture as snow on the top. Okay, so it's actually what it looks like, what a rain shadow looks like if you could look at it from the side and see it happen. Okay, so water on the Earth, okay, the hydrosphere. Okay, so now the hydrosphere still has a fairly big role to play in terms of energy transfers, but it does that through the water cycle. How many times have you been beat over the head with the water cycle? Like almost every year throughout school you had to learn the water cycle. Okay, so in the water cycle you have evaporation, transpiration, condensation, precipitation, infiltration, and runoff. Okay, those are the steps of the water cycle. We'll go over it again. Okay, but we're looking at the water cycle not in terms of I have to know all the parts, but more in terms of where's the energy in and out. Okay, because we're looking at this from an energy perspective. So on Earth, okay, there are many states of water: liquid, gas, solid. Okay, so if we're looking at that, okay, 97% of all the Earth's water is in the oceans, so it's saline. Okay, 3% of it is fresh. Of that 3%, we are looking at ice caps and glaciers being 2/3 of it, groundwater being 1/3 of it, and this tiny little fraction of the rest would be fresh water on the surface. That's lakes and rivers. Okay, where's the biggest storehouse of that kind of fresh water? The stuff that's on the surface and is so good. Canada. More fresh water than anywhere else. Okay, you look at the north of Canada, there's like bogs and lakes and all kinds of stuff. We have more fresh water than anybody else. Plus we got lots of glaciers, which are also fresh water. Okay. All right, so we've got lots of it, okay, but the role of the hydrosphere that at least we're worried about is just transfer of energy. So, energy into the water cycle is the parts that make liquid water turn into a vapor. Okay, so that's evaporation and transpiration. Transpiration is the evaporation from plants as they carry out photosynthesis. So both of those processes put water vapor in the air. That takes a lot of energy. And when the water vapor goes into the air, it takes that energy with it. Okay? Water vapor has way more energy than liquid water because it has changed state from liquid to gas. Now, when that water vapor goes into the atmosphere, now it can move very easily from one place to another. Okay? More easily than liquid water can move from one place to another on the surface. Okay? Because wind can just blow this water vapor around. So if there's a whole bunch of water that evaporates near the equator and then gets blown northwards, when it gets here, it's bringing energy from the equator. Okay? Most of the time we're just getting energy in the form of sunlight. But if we get a big air mass moving in that's got a lot of moisture in it, it's bringing some captured energy in the form of what we call latent heat from the equator here. When that water precipitates or condenses back into a liquid form, that energy gets released. Okay, so it'll increase the energy or transfer the energy from where it evaporated to where it condenses. Okay? Lots of energy actually gets moved in this way. Right? So latent heat, or the energy that's transferred within the water cycle, is a huge part of getting energy from one place to another. Okay, so the hydrologic cycle, the water cycle, okay, is driven by the sun's energy and has been recycling that water for some time. So this here, evaporation and evapotranspiration, okay, that is energy here, where it's condensing and falling as precipitation, that's energy out. Okay, so that could be transferred from one place to another. Okay, everybody all right with that? Now, you still need to know the parts of the water cycle? Yes. Okay, you need to know evaporation and transpiration because that's where the energy is going in. You need to know condensation and precipitation, that's where the energy is going out. Okay, you also need to know surface runoff, so that any liquid or meltwater, okay, that's running back towards the ocean is still carrying energy with it. It's just kinetic. Okay? It's headed back to the ocean. Right? Infiltration is when water goes down through the soil and fills up aquifers. It's how your well, if you have a well, it gets recharged. And it's through the process of infiltration. Okay? That water, that energy is essentially going to be locked away, okay, for a long time underground. All right? Those are the steps you need to know. Okay, we already talked about that. I'm going to skip that one. Okay, and then the lithosphere. Okay? Now, the lithosphere, the solid part of the Earth, has basically no role in the transfer of energy from one place to another. And the reason for that is it doesn't move. Okay? You don't see rock moving from one place to another. Okay? So it doesn't really transfer energy. The only way to transfer energy in a solid is by conduction. That means individual particles physically running into each other and transferring energy. That doesn't happen over big distances. Okay? So the bulk of the transfer on a global scale is in the hydrosphere through the water cycle and the atmosphere through wind. Okay? The lithosphere, the only role it plays is albedo. Okay? So it determines how much energy is absorbed and how much is reflected, and it's also where plants can grow. Okay? So those are the roles it plays. It plays a bit of a part in albedo, and it plays a bit of a part in the conversion, okay, of solar energy into chemical energy by plants. All right, so the role of the lithosphere, like we said, is to provide soil. Okay, that's where plants can grow. Okay, soil is its own little ecosystem. It's got living and non-living parts in it. Okay, and all of that produces the conditions necessary for certain plants to grow. Okay, is soil the same everywhere you go? It's very, very different. Okay, even like from here to Edmonton, soil is going to change a lot. Here, soil is very sandy because our bedrock here is sandstone. You go to Edmonton, there's more limestone in the bedrock. The dirt is darker, finer. Okay, whereas here it's lighter and grittier. Okay, simply because of what kind of rocks we have. So soil differs from place to place. That affects what kind of plants can grow there. Okay. This is the desert, so it's mostly rocks, right? If we're looking at this picture here, what we see for soil is like rock. Not too much is going to like that, okay? But some plants can grow in it. Okay? And around here, we get mostly grasses that are able to grow because they can tolerate dry, sandy soils. You go further north, you're going to get parkland, more trees because they like that loam-like soil. Okay? So the role of soil is to basically determine what kind of plants can live there, which then, of course, determines how much energy gets converted by photosynthesis. In this picture, is much energy being converted by photosynthesis? Okay. Is much energy being absorbed? Yeah. This has a very low albedo. There's lots of dark colors other than the sand flats there, okay, or the salt flats, sorry. But the rest of it is pretty dark in color, which is why, of course, deserts can get very hot. Okay. Does sand absorb a lot of heat? If you've ever walked on the beach in the afternoon when the sun's been on it, right, you can burn your feet. Okay, has a low albedo, okay, it absorbs a lot of energy. Okay, so role of the lithosphere, albedo, and provide soil for conversion. Okay, and soil structure, just so you know, okay, this, I have to teach you this, sometimes I show you a picture of it. Soil is basically divided up into 3 horizons. The topsoil, the subsoil, and the parent material, okay, or the bedrock. A horizon, B horizon, C horizon. Okay? The A horizon is the topsoil. It's the nice blacker stuff. Okay? The B horizon is the clay, and the C horizon is the rock. Okay? Now, how many of you have dug a hole? Okay, good. You haven't lived until you've dug a hole. Okay? So if you dug a hole, okay, you probably realize, or if you looked at like where they dug out, you know, for a hole for a house or something like that, you can see the different layers of soil. right? You got the dark stuff near the top, that's the topsoil, that's the A horizon. Okay, below that is clay, right? If you ever dug a hole, you know, almost immediately you hit clay, right? And it's hard to dig through. If you had a sandbox as a kid, okay, there's clay underneath the sand. Why? Did your parents put it there? They did, trust me, I built a sandbox for my kids. I didn't put any clay in the bottom, but it's only a matter of time before there's clay underneath the sand, okay? And the reason for that is sand grains are big. Clay grains are very, very small, like incredibly fine. If you put sand between your fingers and go like this, you can feel the grains. It's gritty, it's big, okay? If you do that with clay, it feels like flour, okay? It's very fine, almost powdery. Okay? And so what happens is when dust blows onto the sandbox and then it rains, the fine clay particles get washed down between the sand particles and they build up underneath. Okay? So you always have clay underneath your topsoil because clay is made of fine stuff that can wash down underneath. Okay? And get filtered through. Okay? And it ends up underneath always. Okay? So your subsoil, your B horizon is clay, and then underneath that is rock. Here in Okotoks, you can encounter all three in the same shovel, okay? Because our topsoil tends to be very thin, okay? And then we've got clay, and then we've got big chunks of sandstone, okay? Okotoks is built basically on a big sandstone outcropping, okay? So we have actually very little soil on top of that outcropping, right? If anyone's ever tried to like build a fence or something like that, or even dig a hole for a house, okay? Our first house here in town, when they dug the hole for it, they pulled out pieces of sandstone the size of Volkswagens, okay, out of the hole. They had to break the sandstone up to dig the hole for our basement. Okay. Then when I went to build the house, or build the fence around the house, I got this far into the soil, and then I hit the bedrock. How good are my posts? Not very good. I just like filled the holes with concrete and put the post in and went, okay, best I can do, because I couldn't dig any further. Right. Okay, so those are your layers of soil. Make sure you know what they are, okay? A horizon, topsoil. Yeah. Okay, B horizon, okay, subsoil, clay. C horizon, solid rock, parent material, sometimes what we call it, right? So it looks like that, stratification of the layers of soil. Right, so like we said, okay, A horizon is the topsoil. This is a pretty typical soil horizon for our area. Okay, you got your topsoil, you got your clay, you got your bedrock. Right, and so that would be the diagram of it over there. Okay, so A horizon is where everything grows. B horizon is where moisture is typically held. Okay, it's mostly the clay. Okay, there's very little organic material. There's, you know, some roots might penetrate that far, but there's not a lot of living things down in there. And then underneath that is the rocky subsoil. So this is very typical again for our area. You might have chunks of rock even up in the B horizon, even sometimes in the A horizon. Okay. All right. I'm gonna give you guys about a 5-minute break here. Yes, okay, 5-minute break, and then we're gonna get back at this. So basically what we're saying here is that Earth is a system. It's an open system. Okay, because we learned about open, closed, and isolated systems. The Earth is an open system. Energy comes to us from the sun. Okay, things can happen to that energy when it gets here. What are the 3 things that can happen? Reflected, absorbed, converted, right, by photosynthesis. Gotta know those 3 things. Okay, now, the stuff that gets reflected, that goes back out into space. Okay, you might have been told when you were a little kid and they were teaching you about the different planets that planets are like mirrors, they reflect the light, and that's why we can see them, okay? And that's true, right? You can see Earth from other places as well, okay? The Cassini spacecraft actually got a picture of Earth from Saturn, okay, years ago. It's called the little blue dot. The picture is called the little blue dot. You can actually see Earth as a little blue star, okay, in that picture, right? It reflects a lot of solar energy back. It also absorbs a lot of solar energy. Okay. The moon, another one, it reflects a lot of solar energy. That's why we can see it so bright in the sky. Okay. All right. So as we were saying, that light comes in. Okay. A lot of it gets backscattered. Okay. About 6%. Okay. A lot of it gets reflected by clouds. About 20%. Okay. Depending on the time of year, 4% can be reflected by water and land surfaces, unless of course they're covered in snow, okay? At which point they can be a lot more reflective than that. This is actually one of the big concerns that we have in relation to climate change. Okay? What color are glaciers typically? White. Except that lately, they're not as white as they should be, or could be. Okay? In the last few years, we've had a large number of forest fires, and those forest fires have put a lot of ash into the atmosphere, and that ash falls back down onto the surface of the earth. Okay? And over the last few years, dust and ash have begun to accumulate on the surface of our glaciers, and our winters haven't been as long, so a layer doesn't get as thick and deposited on it, so the ice is dirtier. Okay? And if the ice is a bit dirtier, it's the same as what the town does in the winter here when they throw the sand out on the street. Okay? It lowers the albedo of the glacier. The glacier absorbs more solar energy and melts faster. Okay? And that's going to continue to happen as glaciers continue to shrink. More of the darker colored rock around them is exposed. Okay? And that darker colored rock absorbs more energy. It gets hotter. It helps accelerate the melting process of those glaciers. Okay? So we're seeing glaciers recede faster than we ever have. Okay? Back when I used to do a lot of backpacking, we actually came across a sign one day, and it said, in 1901, the Alpine Club of Canada marked this point as the toe of the Rodson Glacier. And we're looking around, and all we see is a meadow full of grass as far as the eye can see. We can't even see the glacier. Okay? And we're talking just over 100 years. It's receded like 3 kilometers in that amount of time. And that's not just receding backwards, it's also shrinking in terms of its height. Right? So we're talking about a lot of ice and snow that's being melted pretty quickly. Okay, so energy in, energy out, we've already talked about that. Okay. All right, once energy gets here, if it's absorbed, it can be transferred from one place to another. So what we want to look at is how does energy get transferred from one place to another? Okay? There's basically 3 methods of heat transfer. Okay? The theme of today is everything comes in sets of 3. All right? We had the atmosphere, the lithosphere, the hydrosphere, absorption, reflection, conversion, and now we're going to talk about the 3 ways energy can be transferred: conduction, convection, and radiation. Okay? So energy comes to us from the sun by radiation. Travels by waves and it gets here. Okay? Once it gets here and it hits something, okay, it can be absorbed. And when it's absorbed, the second law of thermodynamics kicks in. Energy goes from hot to cold. All right? So if I heat up a solid object, then the particles in it start to move faster. Okay? As something's temperature increases, the particles start to move more quickly. The more quickly they move, the more often they run into each other. That running into each other transfers kinetic thermal energy from one particle to the next. And so it can slowly, or in some cases quickly, move along that material, because some materials conduct heat better than others. All right? So for example, if you're going to be cooking soup for like an hour, do you want to use a metal spoon for that and leave it in the pot? No, because metal conducts heat very quickly. The particles in metal heat up, okay? They move really, really rapidly, and the end of that spoon will be hot before you know it. You want to use a wooden spoon, okay? Because a wooden spoon doesn't conduct heat very quickly, okay? All right, so conduction is heat transfer through solids. It's by the crashing of particles into one another, okay? Then there's convection. Convection happens in fluids. That would be air, gases, and water. Okay, and it sets up currents called convection currents, and we use those, okay, to our advantage as much as we can. Right? Hot air rises, cool air descends. You guys heard that before, right? Okay. In our houses, generally, if we're on like the main floor, where are your heating vents? On the floor, because you want the hot air coming out to run into the coldest air first. Okay? Warm it up, hot air rises, cool air descends, you get a convection current going on inside your house, inside the air inside your house, and it rapidly transfers the energy around to the whole house. Okay, it's also why this time of year, your upstairs is gonna be hot and your basement's gonna be cold. Okay, hot air rises, okay, cool air descends, and unless you can keep that thing flowing, okay, you're gonna get one part being cold and one part being hot. Okay, everybody kind of follow me on that? Okay, so this part is gonna be about application. Understanding that heat can be transferred in 3 ways. Radiation, okay, by waves, that's the whole absorption, reflection thing, okay? And then convection, hot air rises, cool air descends, and conduction, particles run into each other. Okay, there'll be a practical application kind of thing for this. Okay, and it'll work something like this. Let's say I ask you to design something that'll keep food cold on a hot sunny day. Okay, what are some properties that that container or device might have? I can't plug it in or anything, it's just gotta try and keep food cold.
Insulation?
Yeah, I would wanna insulate it, okay? Insulation prevents conduction and it prevents convection. Okay, here's how that works. Do the walls of your house have insulation in them? What does that insulation look like? Anybody seen it?
With the pink cotton candy probably.
Yes, the pink cotton candy stuff. That's a perfect, description of it. Okay, but it's not cotton candy. Don't eat it. Okay, it's fiberglass. It won't taste good, and it definitely won't feel good. Okay, so it's fiberglass, and it's tiny little fibers of it. Okay, and these fibers are all intertwined. Okay, so basically what you got is a wall full of all these intertwined little fibers. Okay, what's trapped in between all the fibers? Air. Because that air is trapped, can it move? It can't. That's why insulation insulates. If this is the inside of my house, and this is the outside, okay, this side of the wall is going to get warm because the inside of my house is warm. And let's say it's in the wintertime, the outside is cold. Okay? If I don't have any insulation in my wall, this is what's going to happen. The air next to my wall is going to heat up and it's going to rise. Cold air from next to the outside wall will move in to replace it. This stuff will then descend. Okay? And I'll get a convection current forming inside my wall that will very efficiently transfer all my expensive energy out to the outside. Okay? I definitely don't want that because then I'm just throwing money out the window for my heating. If I have my wall insulated, because the air is trapped between all these fibers, it can't move. So a convection current can't get set up inside the wall. Also, conduction can't occur because conduction doesn't occur in fluids, and there's gas in between all these fibers. Conduction can't occur through that. Okay? So I prevent 2 forms of energy transfer by packing my walls full of cotton candy insulation. Okay? Everybody kind of follow my logic there? Now, are there going to be parts of your wall that don't do that job as well? Which parts? They're about 2 feet apart. Studs, yeah. Okay. When you build your wall, you frame it out. Okay? So you got the top and the bottom of the frame, and every 2 feet is a stud. Okay? A 2x6 piece of lumber. Right? That touches the inside and the outside of the wall. It has to by design. Right? In a lot of houses, if it's really cold outside and you don't have a stud finder, in the wintertime you can just go like this along the wall and you'll feel where the stud is because it'll be cold everywhere where there's a stud. Okay? Because the stud allows energy out by conduction because it's solid. Okay? And it can go through that. Everyone follow me on that? So we would want to insulate the structure, as Ainsley pointed out, because that's going to prevent conduction and convection. Now remember, this is a hot place. What color do I want the outside of this thing to be? I want it to be white, because white will reflect the heat away. Okay? Now, I'm going to show you another example of this. Hang on one second. Anybody ever make a baked potato? Okay, you ever notice that tin foil has 2 different sides? A lot of people shake their heads no at this. I'm going to save you from a lot of embarrassment later. Okay? This side is the dull side. This side is shiny. This side absorbs energy. This side reflects it. When I wrap the potato, which side do I want out? This side. If you wrap it the other way, it will not cook. Okay? It will sit in the barbecue for hours and it will not cook because the shiny side is out. I've seen people do this. I've gone to a lot of barbecues because I like barbecue. Okay? And I like watch them wrap it and I'll just sit there and shake my head. And then when they put them on the barbecue, I'm like, I want that one. Right there. And they're like, why? I want that one. Just make sure I get that one. And give that one to that guy because I don't like him. Oh, because that one will be raw when he gets it because you wrapped it like an idiot. Okay? Now, you didn't know this, so I'm not saying you guys didn't know. Now you know, okay, that tinfoil has a reflective side and an absorbing side. Okay? Anyone ever see the emergency blanket in the kit for a car? The emergency kit for a car? It's tinfoil. Okay? It's got a dull side and a shiny side. Which side should you have facing you?
The shine.
Shiny side. You want to reflect your energy back to you. And a tinfoil blanket does a surprisingly good job of keeping you warm. Okay? All of your radiant energy reflects off the shiny side of the tinfoil right back at you. It can keep you quite warm, even though it does nothing to prevent convection. Okay? Wrapping myself in tinfoil is not going to prevent, hot air rising, cool air descending. It does nothing for that. But it will reflect my radiant heat energy back at me. Okay? Not that you would do this, but like if they were searching for you with an infrared camera, wrapping yourself in tinfoil would make you harder to see. It's also the theory behind wearing a tinfoil hat. Okay? It keeps your thoughts in, and so that people can't read them. I'm kidding, okay? But that's actually the theory behind it. If you have the tinfoil hat, it's so they can't read your mind, because your mind, the thoughts will be reflected by the tinfoil. They're not as crazy as they seem. There's logic to it. Okay? That's how the tinfoil hat works. Okay? All right, so that's the kind of thing I might ask you on a test. I'd say like, okay, you want to keep food cold on a hot day. Or I might ask the opposite. Okay? I want to build something that's going to heat things up quickly. Then I'd probably want it dark in color. I'd want heat to be able to transfer through it quickly. Okay? Things like that. Anyone ever build a Quincy? Okay, so a Quincy is a snow shelter, an emergency snow shelter. All you have to do to build a Quincy is make a pile of snow and then hollow it out. Okay, you don't pack the snow, you just shovel snow into a pile and hollow it out. And you can get it very warm inside that Quincy. Okay, you can get it close to zero, even if it's minus 40 outside. Why? Why does snow, which by definition is cold, keep you warm? It's white, so when you get inside, it's got a high albedo and will reflect your radiant energy back at you. What else? Animals use this.
It's not packed, there's a lot of air.
Exactly. Snow is just like the fiberglass insulation in your walls. The little tiny snowflakes, they catch on each other, okay? And they interlock, and there's air spaces between them. That trapped air can't convect, okay? And because there's gaps of air, there's no conduction through either. It acts as an insulator. It's an excellent insulator. It's why animals will burrow underneath it in the wintertime, because it acts as an insulator, keeps them warm. Okay? So making a snow shelter out of snow is a good idea if in an emergency, because it can help trap heat in the same way that insulation does. Okay? Now, if I wanted to build a solar water heater, as we said, we'd make it dark in color. Okay? We'd probably use materials that would conduct the heat through to the water easily, like copper, or something like that, like spray painting copper black would work really, really well. Okay? And we'd want to circulate it as much as possible to keep putting more water in the sunshine, okay, and getting that energy through. You guys kind of follow how I'm going to ask you to apply that? Just something just like that. Okay, you'd have to talk about convection, talk about conduction, talk about radiation, albedo, all that stuff. It all works together. Okay, so transfers within the water cycle. We talked about this just briefly, but I want to go into it in a bit of detail here now. Okay, so We talked about this thing here, latent heat, earlier, okay? Latent heat is something that's gonna come up over and over again in this unit. Latent heat is the energy stored in water vapor. You don't feel it. It's not sensible heat, okay? It's not the thing you can detect by temperature. It's just there. And it gets released and turned into sensible heat when water changes state from gas back to liquid, okay? Whatever energy it took to evaporate it, it holds until it condenses. And when it condenses, that energy gets released back into the environment because it condensed back into a gas, or into a liquid, sorry. Okay, everyone follow me there? So that's what we were talking about earlier. You can get moisture into the atmosphere. Wind, convection can blow it from one place to another and bring that latent heat to another area. Right? So there's, yeah, we can absorb energy by solar radiation. We can have wind transferring that around, but wind can also transfer latent heat as well. Okay, moving air masses around is an important part of that. Okay, so make sure you know that latent heat is that energy that is part of the water cycle. Okay? It's what happens when water vapor condenses back into a liquid. That water or that energy gets released. Okay? All right, questions there? Sorry guys, I know we're going fast, but we kind of have to. Okay, and then we said for the lithosphere's main job is just to provide soil, allow that albedo, okay, can affect albedo, but mostly it is allowing plants to grow, and plants play the role of converting solar energy into chemical energy, okay? Okay, so back to the idea of that question I told you about where I take a picture of the Earth from like Google Earth, okay, and say, okay, what's going on with the light here, all right? You have to look closely at that picture. You have to only talk about what's in that picture. I've done this in the past, and I've said this is a section of prairie near Okotoks. Sometimes it even has the big rock in it, okay? And then people will write on there, well, the light could hit solar panels, because there's, you know, the solar community here in Okotoks, and some people have solar panels on their houses. And then I say, are those houses in the picture? Okay, they're not. Should you mention that? Okay. Also, is that a natural part of the ecosystem? It is not. So we're only looking at the natural things that can happen to be absorbed, converted, or reflected. Okay? But don't mention solar panels, because that's A, not going to be in the picture, okay? And B, not a part of the natural process. Okay, so I would say write this down. Okay, these are the three fates of solar energy. Okay, reflection, if reflection occurs, there's no energy change. That's determined by the albedo. High albedo, highly reflective. Low albedo, highly absorptive. Okay, absorption, energy is gained and temperature increases, also affected by albedo. And I'll scroll it down in a minute so you can see the other part. Okay, and then the third one obviously is conversion. The process that carries out conversion is photosynthesis. So by plants, they convert light energy into chemical energy or glucose. Okay, that is photosynthesis. So first thing is that I did post the final exam review package in Google Classroom this morning. Okay, so if you go into there, okay, you'll see it, final exam review package. Okay, and since we won't have a lot of time to actually do a review, final exam review for each unit, I posted recordings of those from previous semesters so that you can watch them if you want or need or have time to. Okay, they're there. Obviously, you don't have to watch them if you don't want to, but they're there if you do. Okay, I'll still do what I can in terms of final exam review. Probably all we'll get to is here's what's going to be on the final, and I'll answer some questions. Is probably all we'll have time to do just because of where we ended up. And then this PDF document here is the final exam review package. It's basically old final exam questions and stuff that's, you know, I've asked in the past along with the answers, so you can check and see if you did them right. My suggestion would be to try and have a look at that, okay, over the next little while, and see if there's anything there that you need to come in and ask questions about at lunch or at nighttime or after school, because I don't know if we're gonna get it like an actual, or how much in-class review we'll get. We might get one class, maybe 1.5. And then obviously during exam week, I don't know if I'll even be available This room is being used for a lot of tests. I have my own supervisions that I have to do, and your test is very early. So I don't think that there'll be an opportunity to have like a big, come in and we'll do a big review kind of thing. I don't think there will be. So make sure that you are coming in and checking in with me if you want help on anything, okay, before obviously the 20th of June. Okay. As I said, the unit exam for this unit is going to be June 13th. Okay, so that's coming right up a week from tomorrow, I think. Yeah, a week from tomorrow. Okay, so we'll be zipping through this unit very quickly as I did today. We'll probably do 2 lessons tomorrow, okay, just to get through things fairly quickly. The next 2 things that we'll be going over do involve a little bit of math, but after we've done physics, this will seem very, very simple. Okay, so just know that you'll need a calculator for the next couple of days, so make sure that you bring one along. Okay. For your final exam, okay, here's what you need to bring: yourself, your calculator with fresh batteries. Okay, make sure you have fresh batteries in your calculator for this reason. If your batteries go in your calculator when I'm trying to clear it, because before your final exam I'm going to come around, if you have a graphing calculator, I'm going to clear the memory in it. If your battery is low, I can't clear it. It'll just tell me low battery, which means I will put your calculator in my pocket, and I will go around and clear the rest of the calculators, and then I will go and get some batteries and put them in your calculator and clear it, and then put your dead batteries back in it and bring it back to you. That could take 5-10 minutes, and I think that would be very, very stressful if it were me to be without my calculator on a final exam for 5 or 10 minutes. So put fresh batteries in, and then there won't be a problem.
But if you have like the rechargeable one.
Oh, just plug it in, make sure it's fully charged then, yeah. Just do whatever you can to make sure that your calculator is not something that's gonna give you trouble on the final exam. The best way is just put new batteries in or plug it in the night before, make sure it's charged, okay, so that it's fully functional. Okay, so yourself, your calculator, a couple of pencils, a couple of pens, just in case, you break a lead or something fails or whatever, you got a spare, right? Because there's nothing worse than, you're writing, you're on a roll, and then you snap your pencil, and it's the only one you brought. And now you gotta put up your hand, Mr. Coderre, can I have another pencil? And then you lose track of what you were doing, and that's no good. Okay, if you're on a roll, you wanna be able to keep that roll going. Okay, so bring a few writing utensils with you to the exam. Do not bring your periodic table and formula sheet. You will get fresh ones for the final exam. Okay, because I don't know by this point how much stuff you've written on yours, okay, but you will get a fresh one for the final exam. Okay. Advice. Okay, you've written one set of final exams already, okay, so you kind of know what to expect of it. But my suggestion is this: study often in short intervals. Okay, cramming is one of the worst things you can do in terms of exam preparation. Okay, study in little 5 and 10 minute segments. Okay, that's going to be way more effective and easier for you to plan, honestly. Here's some easy things to do before your exam. Get a good night's sleep. Okay, be surprised how much better your brain works when it's not tired. Okay, eat a good breakfast. Okay, your brain works better when it's well nourished and well hydrated. Drink lots of water. Okay, all those are easy things to do. Right? Show up on time. Okay, I've had people show up for their exam really late, like almost to the point where I couldn't even let them in anymore. By the way, if you're more than an hour late, you're not writing your test. Okay, after 1 hour, people can leave the test. If you haven't come by then, you are so out of luck, okay, on that test, because you can't write it now. All right, so make sure you show up on time, okay, because if you show up late, show up at 9:50 when the exam starts at 9, guess what time your exam ends? Same time as everybody else's exam. Okay, it's over at 11. Bad people do that too. Whoa, don't I get 2 hours for this test? Yep. If you show up on time, you get 2 hours. If you don't, you are finished at 11. I don't want that for you. Okay, so make sure you show up on time for your test. Exams start at 9, okay, but be here for 8:45 or even a little bit earlier. The doors usually get opened and allow you in 8:45, 8:50. Okay, come in and look for your test. It'll be laid out in alphabetical order, and you guys, I believe, are in this room. Okay, so come in here. The desks will be arranged differently. Okay, but A will start at the filing cabinet. Okay, go down that row, and then there'll be another row alphabetically. Okay, find your test, sit down at that test. Okay, and yeah, take your time on the test. Okay, you can leave after 1 hour, but I would suggest not doing that. Okay, it has not worked out well for 99% of the people who have left after 1 hour. Okay, it's a 2-hour exam, so use your time effectively. What else was I gonna tell you? Yeah, you have to stay for an hour, okay, but it's a 2-hour test, so stay for 2. Test should take you between an hour and a half and an hour and 45 minutes if you do a good job of it. That gives you time to check it over and all of that. Okay. What else can you bring to the test? You can bring, food and water and whatever else if you want to, but make sure that it is considerate of others when you bring it. Okay, I've had people make some really bad choices in terms of the things they've chosen to bring with them to the test. Obviously, the phone can't come with you to the test. Okay, it has to be left elsewhere. But if you're bringing food and something to drink, just make sure that it's not going to disturb anybody else. I've had people bring like a 500-gram bag of Doritos to the test, okay? And like we had to take the Doritos away because there were people, I kid you not, who were going to jump out of their chairs and kill that person. Crinkle, crinkle, crinkle. They also chewed with their mouth open, which was really annoying. Okay, so yeah, it was like really disruptive to everybody else. Okay, so if you're gonna bring something to eat, like bring a granola bar. You don't need a huge meal, which by the way, I've also seen somebody bring. Okay, they brought a cooked chicken. Okay, like literally, still hot cooked chicken from Toby's, and some potatoes and gravy and vegetables. Like it was literally a 5-course meal. Okay, I don't know when they intended to write the test. The whole gym smelled like cooked chicken. Okay, which I like cooked chicken, and it smelled good to me, but some people don't like that. Okay, and it's really distracting for them. So, again, bring something that's not going to make a lot of noise, not going to have a really strong smell. I once had a person bring in a grapefruit, okay, which, they were thinking, I want something healthy, and then as they peeled it, they realized it was really fragrant, everybody could smell it, and then their hands were too sticky to write anymore, and they had to wash their hands. So a granola bar is a safe bet, a banana is a safe bet, things like that. With a bottle of water, and as opposed to a, giant Slurpee, okay, give you a brain freeze and then you can't concentrate, stuff like that. So be smart about it, okay? June 20th, okay, 9 a.m. I'm pretty sure you guys are in this room, okay? So just be ready. And reminder, you gotta have your assignments in, okay, by next Thursday at 3:20. It's the last time anything will be accepted, so make sure you have it by then. Okay, and then unit exam the day before that. So on that Thursday, we will go over the Unit 4 exam. We will start our final exam review after that, so I'll probably review chemistry that day. And then the next day, I'll try and quickly review bio and physics and take any questions that you have. The best thing you can do for yourself for those days is to have questions for me. Okay, so the day we're going to be going over chemistry, if there's something you don't remember how to do, ask, and I will demo it, okay, and go over it. Okay? But the more prepared for the review you are, the more you will get out of it. Okay? I think that's all I have to tell you. Okay? You got 5 minutes, maybe now's a good time to have a look at that review package and see what's there.